Hello, it's Wednesday, the 17th of January. I'm still not very good at pointing at things because everything's mirrored here. So I watched a video the other day from Ben, who is the guy that created the Me arm, robot arm, and he was having the same problem pointing at stuff behind him. So I think it's a common issue here. But anyway, we are here today to do some tracking of the International Space Station. We're going to do it on a little e-ink display. But in common with some of these other streams, I'm also going to cover like what else has been going on since the last one. The last set of streams I did was about the little M5 Atom devices. Those are MicroPython. They've got a button and they've got a load of LEDs and all that stuff. And we had some fun with those, and we put some growth sensors on them and so on. So what's happened there since last time is, let me just go ahead and share the desktop. So what happened there since last time is I have, there we go, got written up this project a little bit and put it on my website. So there's a little page there for this. So if you want to see that, go and have a look at the website there. So, and that's got all three of the episodes that we did about this. So in the first episode, we put MicroPython on there. In the second episode, we did something with the accelerometer, the like tilt sensor. And the third one, we did something with the growth sensor with a pack of sensors that I had before. So that was fun. And hey, it looks like Ben from Meom is around this morning. So Ben's across the city from me. We both live in the same city, but on different sides of it. So hopefully at some point we'll do some Meom stuff on here and maybe get somebody else that I've done some stuff with in the past, a guy called Piers, who wrote some MicroPython for the Meom. So that'd be kind of on brand for what we're doing. So if you want a robot arm, go and have a look at Meom. And get it from Meom as well. It's open source hardware, so other people can make it. But if you get it from the creator, then benefits. That's a good thing for everybody. So yeah, so that's one thing we've done is we have finished that, and then I actually sold these two devices on Twitter, and we're still going to call it Twitter on this channel. We're not having any other names for it, so that's where you can find me there. And sometimes after I'm done with some of these devices that you see on the stream, I will move them on, and I'm trying selling things through Twitter, unfortunately to UK only folks because of issues with international postage. And some of these things, frankly, aren't worth posting internationally. You wouldn't get value for your money. So some of this stuff I've been selling on, I sold on the advent calendar that we did the project with. So, whoops. That's the wrong tab, isn't it? That's what happens when you whack the keyboard with the side of your mouse, apparently. I did a project with the Advent calendar here over, funnily enough, Advent, and that's been sold on to somebody else on Twitter who's enjoying that. And then the other thing that I've done in the meantime, in between streams, is I built the little Lego set. I actually built that. There we go, pointing at things again. I built the Lego set that you see behind you, the tiny creator shuttle, a little while back, and finally wrote that up. And kind of the fun with this was I went to Lidl, which is a German supermarket over here in England, and they have this section called the middle of Lidl where there's like all of these things that aren't food. And they change those over quite regularly. So there's some sort of like, ooh, I found a bargain, I must get it now. So yeah, well, I was in there for bananas and a pan of raisin that you can see here. We also got a space shuttle. So that got built. And if you want to watch that done in 3 minutes, there's a video on the website. So again, everything will end up on the website. It might take a little while. What else have I been doing? So I said I'd sold some sensors. Obviously, if I've sold some sensors, right, that means it's time to get something else. So I came across this project this is actually from the guy that created the RPi Raspberry Pi locator website. So during the chip shortage, if you were trying to find a Pi, especially when the Pi 4 was the sort of current best thing, before the 5 came out, there was some major supply channel issues and things sort of got slowed up for a long time. And it was very hard to get these things. So this guy behind this project created a site and basically obsessively tracked and scraped the suppliers, and those that didn't want to be part of this, he removed them from. So it's kind of a by permission thing, and tracked where you could get a Raspberry Pi 4 or other boards, so like the compute module or the 02. And importantly, where you could do it at retail price. So you could always get them at price gouge prices in Amazon or eBay or the other places, but he wanted to track retail price. And he's done something that kind of interests me. He's built a product out of the Pico W, the little Raspberry Pi microprocessor. And that's relevant to what we're doing today. And it's got a web interface for configuring it and getting data out of it and all sorts of stuff. And he's got an MQTT interface, and you can see some examples of, let's make it bigger, some examples of that here. And one of the things that I've been building with today's project, the ISS tracker, which also uses a Pico W, is an initial setup process. So if you got it in the mail from me, say you bought it or you download the software and installed it and you gave it to someone who's not very technical, I wanted a process where they could come to a website on the little device, configure it because it needs to know your Wi-Fi details, and then have it reboot and connect to the network and do its thing. So he's done something similar. So I've got one of these coming because I'm really curious about how that works. And also, he's gone with CircuitPython rather than MicroPython. I haven't done much with CircuitPython. It's kind of Adafruit's version of things, and it looks really good. The primary difference from a sort of workflow perspective seems to be that you plug the CircuitPython device into the computer, and it basically becomes a drive. So you can just drag and drop stuff onto it. Whereas with MicroPython, it's a little bit different. You have to use tools like MP Remote or the Thonny editor, or basically things to move and view files. So that's interesting. And this does air quality sensors. So you can buy it, by the looks of it, without the sensor built in, or you can add the sensor, and that adds $22. And you can add some headers if you want to connect some other stuff to it. So I went with the sensor and no headers. And we'll see when that shows up, and it might make its way onto the stream at some point. Like I say, I'm really interested in the sort of productization of these devices. So there's companies like Pimoroni making devices that have these Pico Ws built in. I have a few of those here, and that's what we're looking at today. And then I'm kind of interested as a software person in what can you put on top of these and kind of make them a product that someone receives like they would buy, I don't know, an Amazon Echo or something, and then has a configuration process that does useful things for them. So yeah, so that's been what's happening in between times. There's also some boring stuff, like I've got to renew some car parking permits today, but never mind. But what we're here for today is, let's make this bigger again. This has been on the stream before because I have used it with the big bus sign behind me to do some plane tracking. And it is an e-ink display that is built, that has a Pico W built into the back of it. It's like soldered on, so you don't have to do anything when you buy one of these. It's just all ready to go. It's from Pimoroni, and it costs £33, or you can get what they call an accessory kit, which gives you like a picture of the accessory kit. Maybe if we select it, there we go. So the accessory kit gives you a battery box and some Velcro to stick the battery box on the back, and a lanyard and a cable. Because this thing is called the Badger W because it's designed to be used as a sort of badge. So you could wear it like at a conference or event or whatever, or trade show, or wherever you want really, and put whatever you like on it. And it's designed to run efficiently and go to sleep. And obviously the nature of the e-ink display is it's semi-permanent, so you can turn the machine off and it will essentially keep whatever's on the screen last. So I've had, I don't know, 2 or 3 of these over time. There's the W version with the Wi-Fi. That's kind of like the one you really want because you can do more projects with it. If you don't need the Wi-Fi, you can save a bit of money and buy the other one that doesn't have it. Basically, the difference is which Pico you get on the back, but you can't change these after you've bought it. So you kind of need to decide and run with the one that you want. So yeah, that's the device we're going to be playing with today. And with a lot of these things, you can program them in basically C type stuff or MicroPython. And we're going to go with MicroPython. So we'll look at what that means and so on. So yeah, let's actually bring the device up. So let's remove that and add this. So this is where we're going today. Well, not physically. We're not going to Papua New Guinea. And you might look at this and go, hang on, I've just checked the space station tracker. It's not there right now. And it isn't. This is a picture from last night. It's the actual device. And what I did was just turn the power off on it. And the display stays as it is. So at the time, it was tracking the ISS. And you can see where the ISS had been. There's this series pointing at something upside down. It's quite confusing as well. There's this series of dots here, with the biggest dot being the last place that we saw it. So what this project aims to do is pretty much what you see, still pointing the wrong way, what you see on the display over there, which is you see, let's make it even bigger. And let's get rid of that annoying banner because it's been up there way too long. What you see is that the device is showing how many miles away from me, so my location, the ISS is at any given point, where it's flying over. So what point of the Earth is it currently above? So here it was in Papua New Guinea. When that was, so you see that was last night at approximately 6:25. And then we've got a map of the world so you can sort of visualize where it is and where it's been. Obviously, given the nature of this screen, it's very small. The scale, there's one finger, so it's not that huge. You can get bigger ones. So we've got a map and we've got limited basically coloring on there. We've got black, white, and sort of approximations of grey. And then we need to put the dot on the map where the thing is. Other features this has got is it's got some buttons. So these, pointing at things is hard, A, B, C, and then up the side there's a couple more. Buttons are programmable, so we can do something with those. If I have more time on this, I could maybe have it switch between different functions. So it might be able to switch from like the ISS to the weather to who knows what, quote of the day or something. Because these things being e-ink, they're good for slower updating things. They're not good for real time. You're not going to play a game on here. The updates are too slow, as we'll see when we actually start to play with it. So yeah, we've got that. We've got this device here. This one's called the Badger. If you did want to do more complex e-ink projects with the same sort of product, then this one's the Badger. If you look at this and you just search the Pimoroni site for Inky, they've got a whole load of these, so up to 7.3 inches. I think this is probably the biggest one. And you can get this one as either a hat if you've got a Pi, a regular Pi, or let's just pick this. I love its shipping containers. You'll notice behind me there's like shipping containers and shipping ships and stuff. But the stock image is shipping containers. This one's got some colors and it's a bit bigger, but it's basically the same deal of on the back there's a Pi W, there's a micro SD in this case, I guess, so you can store some more stuff and display images without having to store all of that data on the little Pico. And there's a couple of up here what Adafruit calls stemmer QT connectors. So you could plug sensors in here and have this be some sort of sensing device that maybe talks to the internet and gets more information, displays some stuff and so on. So these are bigger. They obviously cost a bit more. This one's £90, but you get more screen real estate and you get some colors. Looks like you get about the same number of buttons as well. They're just laid out differently. So back to this one, the other feature we've got is down here by the little heart, there's a user controllable LED. So we can turn that on and off. What I'm using it for in this project is to highlight when the ISS is nearby. So there's like a configurable number of miles that the ISS can be away from you. And when that comes, the ISS becomes within that distance, the light goes on as well as it continues to show up on the map. So you get that extra like, oh, it's relatively nearby. So yeah, we did that. So I'm just going to close this down and close this down and close this down. We've got some source code for this project. So to be frank, haven't done a great job of documenting this yet. It's pretty basic. So I need to work on that, and I'll do that before it goes on my website. But I put a picture in there, and the source is all up to date with what we're going to look at today. So if you wanted to use that, it is at the URL at the bottom. It's also in the video description, and it will get better. I want to finish this so that I can do another article on my website for it. And I tend not to put things on the website until the GitHub is properly finished and done. Also, because writing these READMEs kind of helps a lot with collecting your thoughts for the website. So one leads to the other. So yeah, we've got that. And basically, we are going to build or look at how I've built something that is a bit of a product. So there's two parts to this. There's like getting the ISS information and displaying it on the device. But there's also getting the device from a sort of factory state where if I shipped it to you, I don't know your Wi-Fi SSID and password, and I don't know where you live. And you shouldn't need to give me those things as part of me being able to ship you this device and you to set it up and enjoy it. I don't want to know your secrets. Imagine if you bought, I don't know, an internet connected plug or something, like one of these things that's this is a Tasmota plug for a future stream. And you had to tell the vendor your SSID and password so they could pre-configure it. That's ridiculous. So what I've been interested in with these, and why I was so interested in the Tindy project with the environment sensor from the RPi locator guy, is that it makes it more of a product and there's a setup process. So I want to look at that too. So we've got this, we've got the ISS tracker repo, and we'll go through that. We've also got Pimoroni's Badger 2040 repo here, which gives you a few things. It gives you documentation and example code for how to work with the thing. And it also gives you MicroPython UF2 images. So this comes with MicroPython pre-installed if you go and buy it. But if you want to make sure that you've got the latest version of whatever they've been up to that's specific to this device, then you can come find that here as well. We won't install MicroPython on this because it's already done, but it's the usual process of press the boot cell button on the Pi, connect it to the computer, drag the UF2 file on there, and watch it go. So there we go. And bonjour. Thank you very much. Hopefully this is going to work so we can actually show you how it works. Because at the minute it's turned off from last night, so this is static. It's not changing. Great. So this is Pimoroni's Badger 2040 W. What I love about all of these products is you can have any of their sort of Pico inside products, and they use a common drawing library. So if you've got, let's make this happen like this. So if you've got this one that's e-ink, then, and you understand the drawing library, then you can kind of work with this one that is LEDs and same Pico W on the back. And generally, if you know how to draw a rectangle on one, you know how to draw a rectangle on the other. And there's obviously some differences, speed of update, colors, that sort of thing. But they've done a really good job of producing a standard graphics library that works across all of these devices. The other thing that I have for this device is you notice this one here. This is a unicorn class device. They come in 3 different sizes. This is actually the smallest one. There's a bigger one and there's a longer one. And this has legs, so it sits on your desk quite nicely. And I played around with taking this apart and putting the legs from that in the holes of this guy. And if you put the legs from the unicorn in the top holes here, this sits nicely on your desk, like sort of. Remember when you used to go to somebody's desk, like I don't know, receptionist somewhere, and they'd have their like nameplate on the desk. It sits nicely like that, so you don't have to mount it in anything. I'm using it flat today because the camera's overhead, so the camera's going to point down. But I did ask them to put the legs in the store, and I'm not sure if you can buy them yet, but at some point the legs will be a thing you can buy, and they're just these nicely beveled screw things that you put through, very easy to attach. So I'll put that back on the camera. That is upside down to me, which is confusing, but I love how clear it shows on the camera. There's no glare or anything because of the nature of the ink. And it's probably inevitable I'll get one of those big color ones at some point and do something bigger with it. But for now, we are going to stick with the little one. So again, there's a bit of sort of run up before we do anything here, but I wanted to show the end state of what have we built and then sort of work backwards to how does it work. So for that, I actually sent a couple of these units to relatives over Christmas as presents. And these folks aren't really technically aware. They're certainly not going to be like, oh, install Sony and mess around with MicroPython and edit a secrets file that has your SSID and your password and all that stuff. People aren't going to do that. So what I did was I wrote a manual. Let's see if we can make this bigger as well. So I wrote a manual for them and printed out a copy and sent it and built this whole setup process and basically told them absolutely nothing about the devices. So I was just waiting for the device when it's running talks to Google Cloud. So I was waiting for things to start pinging my Google Cloud, and then I know we've had success and it works. So we put a little bit of background about why this is called a Badger and the company it comes from, and it's a relatively local thing to us. It's from Sheffield, and so on. So there's some blur about the space station, but basically I gave them a little how to build it. So how to attach your legs, how to shove in a USB cable, go find your own power supply because I didn't supply one of those. Everyone's got some sort of USB phone charger and they work great off of that. So I left that to folks' imagination to do. And then what we did was I built a process where when you get it, in some cases, I did pre-configure it for their SSIDs because they're relatives and I already know the information because I go around their house and I'm on their Wi-Fi. In other cases, I didn't. So let's just skip ahead a bit to okay, what if this device wasn't pre-configured? Imagine you just bought it from a shop or I'd shipped it to you because you bought it off of my website or Tindy or whatever. I don't have those things. I'm not selling these things at this point. What would happen is you would power it up and it would start a Wi-Fi access point. So it would be like, oh, connect to the network called ISS tracker. So it's a bit like when you buy a new printer or a new Bluetooth speaker or Bluetooth speaker is not a good example because that's Bluetooth. Okay, you buy a new printer or a new security doorbell or something and you need to connect it to your Wi-Fi. So you can connect this to, but it exposes a Wi-Fi that has a known name. So you then connect your phone or your laptop or whatever else to that. And it's a bit like you're in a cafe. So when you're in a cafe, something pops up immediately and is like, oh, welcome to the cafe. Do you agree to our terms and conditions? What you get on the internet. That's called a captive portal. And you can do that quite easily with the Pico and with another Pimoroni software framework that we'll look at. So that's what I did. So basically what happens is you then go with your device. So this is an iPhone, but it could be anything. And you connect to that ISS tracker network, and it pops a little web page that I put on there. This is a little bit of an old picture by the looks of it, but it pops a web page, and what happens is you tell it your Wi-Fi details. And I actually improved this since I took the picture. So instead of this just being an empty field, it's now a drop down. So it scans the Wi-Fi on the Pico and it figures out which devices or which networks it can see. It ranks them by signal strength. And then the top one is most likely yours. So it puts that first. And then if it can't see yours because you don't publish the SSID or something, there's an option to just enter it. So they need to enter the SSID and the password. And then they need to enter where they are. So where in the world you're located. I used a couple of examples from different places in England. And it needs this so it knows when to turn that light on and to get that, pointing at things is odd, that big number down there, how far away the ISS is. It needs all of that information to calculate that. And then you basically hit save and the device reboots. And if you put in some good information and it connects to a network, it starts up and you get this process. So you get a nice image of the space station. It says it's connecting. So you've got something to look at while it's doing something. Then it'll say connected and it will go off and track the space station. And we'll look at how all of that works. So I wanted to have that process down and working and something that I can use again in future products. So I'm pretty pleased with it. There's a couple of other things that I did here. If you hold down the A and the C buttons together, it wipes out the Wi-Fi configuration and the location and reboots and goes back into the setup cycle. So you've got the option for like, oh, I moved house, or I changed my Wi-Fi SSID because I got a new internet provider or a new router or something, or I changed the password because periodic security. So it's designed to live in someone's house that isn't very technical and basically not be a pain for them to operate. And it seems to be doing a good job of that. One of these has been operating for quite a while and it's happy. So yeah, that's what we've got, is all of these. Then like building this down here, you have to build a little web server on the Pico and serve the pages. And also, you kind of want to give them some level of styling, but you can't really go crazy with it because this is a captive access point. Pico doesn't have access to the internet at this point. Neither does the device that's connecting to it because it's on this little Pico's Wi-Fi. So you can't go off and like reference a load of style sheets on a CDN or something. You have to put everything inside the device. So I kept it really simple with just something that basically cleans up the styles and makes forms look better than default, because web forms always look terrible when you use defaults, especially on mobile devices. And just styled a button, and that was kind of it. That's a good compromise between going crazy and, you know, if I put a logo image on here and things, I'd have to store that image on Pico, and on this device I don't have an SD card to offload that sort of heavy stuff to, so didn't bother. It's all nice and simple. So yeah, that's our setup. So if that's the end game, then how did we arrive at the end game? And what happens if I actually plug this thing in? So what I'm going to do is look at, this is an ISS tracking site. Or a visualizing site. So there's a site here that will tell us where the ISS is at the moment. Let's see if we can get rid of that ad. Ugh, we can sort of hide it. Okay, and we have to subscribe. And I understand that. That makes sense. So we'll just live with the ads. So the ISS at the minute is somewhere over the Bering Sea between, I guess, Russia and the United States, but it's heading on a trajectory where it's going to go down the Pacific and it's going to be over the ocean for a while. And that's actually one of the complications with building this, is the amount of ocean that we've got and the amount of time that ISS spends over it. But we'll figure out why in a minute. What I'm going to do is apply power to this and see what happens. I'm also going to apply blue tack to it so it doesn't move around. Hey, there we go. So what you see is as it updates, it kind of flashes a little bit. It's booting up. It was already connected to my, or configured for my local network here. So it's connected to that. And it's going to now go think about where the ISS is. And then hopefully it'll draw a map. There we go. And it is what, 5,405 miles away from me over the North Pacific. And let me just make that big so we can see it a bit better. Put it in the camera's view a bit. You can just cheat and move the map. You don't have to move the maps. You don't have to mess with the device itself. So that's where it is. On our map, it's kind of off the edge of the map at the minute because our map doesn't recenter as the ISS moves around. This one keeps the ISS pretty much in the middle of the map. So yeah, that's where we are. Nigel has a question. Is an individual Google Cloud account needed? Well, yes and no. I'll come to why, but the long and the short of it is I offloaded a lot of the processing and the calculations from the device to the cloud for two reasons. The device is little and not very capable, and it slows it up, making lots of network requests to the different services I needed. And I wanted to build something where I've got a service that provides the same information to a whole load of different devices. So you could render it on one of these or something else. I didn't want to have to rewrite that logic or bundle it up as a MicroPython library. Or even I wanted to be able to use it from like the web or something as well. And there is a little complexity that means you need multiple services to get all the information to pull the information that you see on the screen there. And I'll come to that. But the long and the short of it, the short answer is there's a single Google Cloud function that you can run. There is nothing Google platform specific to it. You could run it elsewhere. So if you like running AWS Lambdas or whatever, as long as it's got a URL that the device can reach, and as long as you've got a key for the Google geocoding API, then it's going to work. You could build all of that into the device. I just saw it as unnecessarily complicated and also meant I would potentially be repeating myself if I built other devices in the future, or like if I wanted to use the bus sign or something as a client for this. So I sort of went logic in the cloud, display on the device, and separated the concerns. So I'll come to that as well. So that's it working. We've got a thing here, and as you can see, it isn't actively doing anything right now. It's going to sit around for about 5 minutes, and then you'll see it flash and update to wherever the ISS is next. So what we've got to do here is basically do some getting of data and then some translating of data from one set of things to another. So what you see on the screen here is a JPEG image of the world. And the JPEG image doesn't understand that long coordinates. You know, it's got pixels, so it's got like 0 to however many pixels wide it is in the X plane and 0 to how many pixels tall it is in the Y. But the world doesn't quite work like that. And neither do the data services. So what we needed to start with was, let's just flip back to a better view for this. That one. What we needed to start with was some sort of service that tells us where the ISS is. And over here, there's this thing at Open Notify that seems to be the one that a lot of people use. And it does one job very simply. It tells us where the ISS is now. It's got a very simple API for JSON. You just hit this URL. It's not even an HTTPS URL, although you can get one. There's probably good reason for keeping this as HTTP. If you're going to use tiny devices, they don't have to deal with the SSL impact. But what this will do when you hit it is we get back a JSON payload, and really what we're interested in is this bit, which is a latitude and a longitude of where it is. As I understand it, that's calculated from knowing the orbit and just doing the maths. So if you know the orbit and you know the current timestamp, you should be able to do the maths and figure out where it is. You know, there's no like radio packet tracking thing like there is with the aircraft. And if we hit this, then what we should see is we'll get a current value back. So I'm going to swap over to Postman, the API tool, and I've got a little collection here of all the badge updated, so it moved. So we're now North Pacific Ocean and 5,912 miles away. It's also wrapped around. It's on the other side of the map now. So to get the ISS position, we have to go to this URL. There's no security or anything, so we can just request it. And let's get. Can you show this nicely? There we go. And we get basically what they told us we would get. We get an ISS position object, and this is the current longitude and latitude. It's at minus 155 and a bit and 38 and a bit, which turns out is a position over the North Pacific. So what we have to do with this is all well and good, but the information we want looks like this, right? So we want a distance from us. So we're at a latitude, longitude, and ISS is over a latitude, longitude. How far away are those two things? We want a name for that, so it means something to people. And we want to plot it on our little map of the world here. So those things we can't do with just this information here. So this information here, and let's see if we can make that bigger. It's still Command plus in Postman, okay. This information here is not much good for that, but it's a starting point. So once we've got this stuff here, we then have to do something to make it meaningful as to where is this in the world. And the sort of service that we use for that is what's called a geocoder. It can do multiple things. It can take an address and tell us what the lat long position is, or it can take a lat long and have a stab at what address or what town or city or location on the Earth that maps to. So I am using the, let's make this a bit bigger as well, the Google Geocoder API here. So this is one that if you've worked with Google Maps, you've probably used before. It's a pretty common one, and you just get an API key and you get so many usages of it. So if you were to answer the earlier question about do you need a Google Cloud function, if you were to run this elsewhere, you could swap someone else's geocoder in if you wanted to, or I'm just calling this across the internet at a URL with an API key. So Google doesn't really care who's hosting the code that runs that. I'm just happening to host it in Google Cloud because it's a place that was convenient. So with the geocoding API, that's basically going to take, this is what we want, one of the functions it does. We want an address for a set of latitude and longitude coordinates. And we don't really want a full address. You know, we don't want a postal address for where the ISS is over. We want to know roughly the town and the state if it's in a country that has states and the country. And then we also want to know, back to this map, there's a lot of blue here. So a lot of our planet is the oceans and the seas, and the ISS therefore spends a lot of time flying over these things rather than the land. And the oceans and the seas don't have street addresses because nobody lives there. So we also want to know ideally what ocean we're over and what sort of part of it if we can. So you'll see right now it says North Pacific. There's a little bit of a complexity with getting that we'll look at. So if we have a lat long and we have the Google geocoder, then we can call it and get some information back. So I've got an example call here, and what you'll see is I go to the Google API location, and we tell it what I want back. I want a country, a locality, some other bits and bobs, an administrative area, some natural features. I want them in English, and I tell it where I want it to tell me about. So this is a location on the Earth, and this is a resource protected API. So I have to give it a key, and that's a secret in my Postman collection. So you have to get your own key, but you can sign up for free. And what will happen is when we hit send on this, it'll give us some information back as a JSON document about this place. So what have we got here? We're not really interested in that stuff. We're interested in the results. So we could potentially get more than one result, but generally the first one's going to be the most accurate one. So this place here is actually, it's Longreach in Australia, which is there we go, it's in Queensland. So Longreach in the state of Queensland in Australia is a fairly remote place that I think is known for, I think Qantas was founded there, the airline. So yeah, we've got a place Longreach in Australia, and from the lat long, we've been able to get information about it. So if it had a very, very long name, Google can also give us a shorter version of that name, and that's useful on things like this, where we have got limited screen real estate. And it looks like the camera's decided to defocus there. So let's just see if we can bump it. Come on, camera. Assuming me. Let's wake it up a bit. There we go. It's back in focus. So it decided to defocus. It is set to a manual focus, which is weird as well. So it shouldn't really do that. But anyway. So our geocoder gives us information about where we are. If we're over a more populous place, we might get a street name or all sorts of things. But these address components have fixed names. So, there's a long name, long reach, and a short name. And in this case, they're the same thing. And then we can go down here and we can see that this is an administrative area. So Longreach is contained in Queensland. That's the Australian state that it's in. And we can use that to build up information. So this is great. And this is going to work really, really well. So I said there's a complexity with the ISS spends a lot of its time over the ocean. So as you can see right now, it's over the North Pacific Ocean. So in theory, if we took the Google geocoder here and we give it a position that's in the ocean, so this lat long here is not over land, then what you might expect to happen when I hit send on this is I get back information about the ocean that we're over, especially as I've asked it for a natural features layer. And as it turns out, what actually happens when you do this is computer says, no, you get absolutely nothing. So it doesn't know about the oceans, which seems to be a big hole in what's quite a popular service, if you ask me. I did Google around this and didn't find anything useful. So what I've had to do and why I started moving some of this stuff to a cloud function off the device was, okay, we'll call the Google, we'll get the ISS location first. So we'll use this API. We'll get a lat long from having no knowledge at all. We just send it this. And then what I wanted to do was, in the event that we get some results back from Google, so we're over land, use those. In the events that this happens, so we're not getting any results, then now we have to do something else. So we're up to making what? 1, ISS position, 2, Google, see if there's any results, potentially a third call for the ocean. So this started to look better in the cloud where it could scale and take it off the device. And it was getting to be a lot of logic that you would have to reproduce on different devices. So I went looking for, well, okay, what knows about oceans? And I still wanted to stick with the Google geocoder for the majority of things. And I hope they fix this at some point. But there's a service called, this is very small, GeoNames. And GeoNames has all of these different web services, and they're available in XML if you really don't like yourself, and JSON if you want to work with things easily. They also have a geocoding type service, but the quotas for Google were better, so I stuck with it. But what's important is they have this ocean service here. If I click JSON here, what you'll see is the daily credit limit for the demo has been exceeded, and I expected that to happen. So they're also a protected API, and you have to register and get a username that is a secret. So when you pass in a username, so see here, this username equals demo. That's kind of hard to see up there, but there's a demo username. And what this will do is it will take a lat long that's over an ocean, and we already know how that long's over the ocean if Google has basically said, I don't have anything for you. And it will tell you what ocean it's over. So if we take this same lat long here that Google said, I don't know what that is, and we go to the GeoNames URL, so we have an ocean JSON endpoint, and we pass in the lat long, and the username is a secret. And when we hit send on that, you'll see that I've got quota for the day. And that is in the Tasman Sea, which is the sea that separates Australia and New Zealand. So it's east of Australia, west of New Zealand. So we've actually got something that tells us something that Google didn't know about. So potentially, to get the information you see on the screen, we need, well, just to get the name, we need 3 API calls. So we need one to get the ISS position, one to make some sense of it with the geocoder, and then one to fill in the ocean name if the geocoder didn't know what the ocean was. So that is all, pretty much all of the remote calls. We got 2 other aspects to deal with. So one is the big number, how far away is it from me? That's easy to work out. There's something called a Haversine formula that you can get libraries for, that if you give it a lat long and another lat long, it will tell you sort of crow flies how far away these 2 things are. So I've just used that, and that's just some library code in the cloud function that we'll look at later. The other thing is, how do we get this lat long onto a map? So we've got, here's a map of the world with some lat longs drawn over it. And as you can see, there's like 0 goes down the middle here. And that's, I guess, the meridian. So that's the sort of middle in that axis. And then there's 0 that goes here, and it sort of cuts through bits of the South American continent and bits of Africa and bits of Asia. And that separates the 2 hemispheres. That's the equator. So lats and longs basically tell us which quadrant of this, if you divided it into a rectangle, which quadrant of this things are in, and then where within that they actually are. So this is all good, but we have got an image of the world. So what you see here is a JPEG image, and the JPEG image doesn't understand lats and longs. Yeah, the plotting library doesn't understand lats and longs. So let's go back here. So what we need to do is translate somehow between lats and longs and the image. And what I'm going to try and do, or the image coordinates, what I'm going to try and do is, let's just bring up QuickTime and try and do something I haven't done in a while, and select a different camera. It looks like it's going to work. So we can do some drawing. This is something that's fraught with danger, and uses a lot of resources I've found on a Mac, especially if you're using Docker at the same time. But we're not today. So imagine we've got, let's select the pen, and let's select cut. So imagine we've got a sort of world image, that is like this big. And our problem is we've got latitudes and longitudes and we haven't got pixel coordinates. So the image is like 0 to whatever the maximum Y is, however tall the image is in pixels, and it's 0 to X. And what we need to do is translate a lat long position into an XY on that so we can draw our little circle for where the ISS is now or where it has been. And we're going to make some assumptions about the map to make this easier. So the easiest way of doing this is finding a map where this point here in the middle, so like this, so that's the equator and that's the meridian. So the 0, 0 point is basically in the center of the image. And then if we know that, we know, let's try changing color. We know that this way is going to be 0 and it's going to max out at, I don't want to get this wrong, whatever it is, 100, 180. So this is going to be like 180 in one direction. And this is going to be 180 in the other direction. One of these will be negative. I guess it's the west one. And then with our other coordinate, let's assume that this is going to be 0. And this is going to be 0. And then this is going to be, they basically run to 90 and minus 90. So what we can do is, I've lost that camera focus again. I think what happens is it updates and flashes, and the camera's focusing on the flashing rather than the staying focused. So let's just zoom in me again. Let's just play around with that in a second. We'll come back to that. But anyway, where were we? So we were putting pixels on the map. So if we can do this and we can have something where we know those values of X, how wide is our image, and Y, how tall is our image, then we can basically say X over 2 is the X point of the meridian, and Y over 2 is the X point of the meridian of the equator. So X over 2, Y over 2 is where the meridian hits the equator. And then we can basically take slices through this. So like each slice here will be 1/180th of the pixel width. And each slice this way will be 1/90th of the pixel width. And this diagram gets to be a mess. But we can basically calculate an XY location. So if we had a lat long, we could work out a number that varies between minus 90 and plus 90. Or sorry, we can take a number that varies between minus 90 and plus 90, turn it into an X pixel, and then similarly one that's from minus 180 to plus 180, and turn that into an X pixel. The 90s are the Ys. And once we've got those two values, we can go, oh, okay, the ISS is currently like here. And the way this project works is it tracks that and draws it on the map, and then it maintains a little list of the last however many, so we can then draw those and show a sort of, oh, it's currently here and it used to be there and it was there before. So you can see it moving across. So I'm going to put the fun with drawing tools away and disconnect this iPad and move it out of the way because it takes up a lot of desk space. Let's see if we can fix the focus on this camera again. So that is a mess, isn't it? So let's try and get the camera to follow me. Hey, that's how it works. Okay. So as you can see, the whole time, well, we'd lost it then. The whole time that we've been talking and looking at this has been updating. So each dot represents about 5 minutes of ISS movement. and it's persistently tracking over the ocean. It's not going over the land at the minute. So we've not seen any land mass information up here. But this does kind of like demonstrate the point that if you had no information, you were just relying on the Google geocoder, you'd just be like, I don't know where it is most of the time because it's over the ocean. So we could draw it on there because we can do the lat long calculation and we can get the XY values. And we've got that map where the meridian and the equator are dead center. So that's all good. But we wouldn't be able to show South Pacific Ocean. We just have to say ocean generally because we know it's not over the land. We wouldn't know if it was over an ocean or a sea or which part of the Pacific, even in this case. So that extra service is kind of good for that. So yeah, that's pretty much everything about how it works. What I was going to do now was sort of show how we built it a little bit and probably start with the MicroPython. So what we're going to do is assume that there's a cloud function that we've written that has all of the data for this. And I will quickly show you what that data looks like, and then we'll look at the MicroPython, how that works, and then kick back to how the cloud function works. Cloud function is written in JavaScript, but that was a totally arbitrary choice. It could be written in Python or anything else that Google Cloud supports. So to do this, what we're going to do is wander over to, let's see if that, yeah, look, it's the update that's throwing it because the nature of the screen is it flashes when it updates, and then we have to drag the camera back into following the focus. So what I'll do is in the next 5 minutes before that updates, I'll stop it running because we want to do some things on here. And I'll keep an eye on whether it's in focus or no. So let's go back to the desktop. So yeah, there's our map. These are our services. We can get rid of those. We can get rid of those. We can get rid of those. That's where I'm running the code in the cloud. It's a Google Cloud function. Nothing particularly Google Cloudy about what we're doing. It could run anywhere if you prefer Amazon or Azure, or you've got your own server or whatever. So we'll get rid of that. We don't need that. And we'll just keep the browser around for usefulness. But what we do need to do is, I said I'd demonstrate what the function that I wrote outputs, and then we'll look at how the MicroPython renders that. So I can start that locally. So I've got a copy of the GitHub repo, and I can run my function that runs on the server locally, and you'll see it runs at, makes it bigger, runs at 8080. Obviously, we can't reach that over the internet, which is going to limit us. But this is just for local testing. We then deploy it to Google Cloud, and we get an internet URL. So let's have a look at what that does. So when I call it, what I built was something that has a name. So it's called ISS locator, and you give it a latitude and a longitude. And those aren't where the ISS is. That's where you are. So your position on the Earth. And what it's going to do is use those to calculate how far away the ISS is, which is that big number down there. So let's go ahead and call it, and hopefully it works. Yeah. And what you'll see is there is a secret in here. So this is out there on the internet. So if you discovered the URL of my cloud function, you still need to pass in a header with basically a password or an API key in there. And if that's not valid, I'm not going to do any work for you. I'm not going to service your request. So it's semi-protected. But what this does is it brings back just the information that this device needs to populate its display down there. So first off, we get the latitude and longitude where the ISS is right now. You might ask, well, hang on, why did you not change that to XY coordinates to plot on the map? And the answer is because I'm trying to make a general purpose service, and I don't know what size map the client has got or whether it's even got a map. So I didn't want to make assumptions. So that work is done on the client. So we have some translation to do. However, I do calculate how far this point, the ISS location, is from this point, the user's location. So we use that Havertine formula to calculate that. We'll look at that later. And we return a numerical distance and then what unit it is as well, just in case at some point I thought this might be a more global product and we might want to pass in like a units parameter up here and get the result in, say, kilometers, if you prefer metric. So I stuck with miles for now. And then what you get is when it's over the sea, you get an ocean field with the name of the ocean. And when it's over a place, you get an object that has information about the place. So, it might say Longreach, Queensland, Australia. And those will all be in known fields. So it's all been parsed out for the front end to just basically go, oh, if it's got this field, display it, otherwise display that field. And then we tell it when it was updated, and we do that as both a displayable string, which I just used in the thing, and the timestamp in case a different sort of front end wanted to take the timestamp, do its own thing with it. So this is the data that comes back from my service. We'll look at how my service works later, but what you can assume for now is it calls the ISS position API, feeds that into the Google Geocoder. If it gets nothing back from the Google Geocoder, it calls the GeoNames API to get the ocean name. And it also does some slight data massaging on some country names and things. And there's reasons for that we'll look at a bit later. But basically, from the MicroPython, there it goes again. It's out of focus again. From the MicroPython perspective, I said I'd turn this off in the next 5 minutes. We talk too long. But you can see it's getting a nice track down the west coast of what's now South America, but the west coast of the US as well. From the MicroPython perspective, it just calls this and displays whatever it was told. And then there's some complexity about that setup process for I've just got one of these devices. I need to turn it onto my Wi-Fi. So let's get rid of Postman. And let's also try to think what the best. I've got VS Code because there's like a JavaScript and a MicroPython component. And let's use Donny here because it's just easier to drive a MicroPython backend. And let's change over to the ISS tracker project here, and all my Badger code is there. Right. So this is Donny. It's a MicroPython IDE that we've covered on other streams. And what it basically allows us to do is connect to the Badger here, and that's now stopped whatever was running. So we've got a Python REPL on here. I can just put Python stuff in here. That's running on the little device. And that's basically stopped it running, so it won't update anymore now. But because it's e-ink, it's persistent. So the last thing on the screen will stay on the screen, even if we pull the power out, until we tell it to do something else. So that's one of the fun, reliable things about this. So the majority of the fun with this device is there's sort of two things. There's how to draw on the screen, which uses the Pimoroni graphics library is for this, which is, like I say, if you know how to use it on this, you know how to use it on that, and you know how to use it on their device that talks to HDMI displays. But they've all got their own specialisms, but the basic core is the same. So the way that the graphics library works is it has the concept of pens, and you use pens to draw on the screen, and you can draw shapes, and you can load images, and you can write text, and text has fonts. So it's all fairly straightforward. And hopefully we can demonstrate some of that by bringing up the code that the ISS tracker is running, but not running it. What we're going to do is just play around with some of it here in the REPL and see if we can get the screen to do some stuff. So first off, we're going to need Badger 2040, which is the module for this device. We're also, I don't know what else we'll need, but we'll just mess around. So let's first off see how this works. So we need to initialize a display. So that's like a thing that we're going to use to write things. So we just create a new instance of Badger 2040. With these e-ink displays, you can set different update speeds. I'm not sure what the difference between those is, as in, is faster sort of dirtier and less reliable or what, but whoops, you shouldn't be using these for like time critical stuff anyway. So we're going to go with a normally updating display, and this just turns the LED on the device off. I don't need that. The LED's off already. And then this sets a font on the device. So let's use that because we'll write some demo text. So we've just got some preamble here that set this up. And let's see what other interesting code we've got in here that we can mess around with. So the way that the graphics library works is it has pens, and pens have colors, and you use them to draw things. So you can see here I'm creating a pen with, or I'm setting the display's pen to be pen 15, which on this device is basically erased the background color. And then pen 0 is black, so the one that we're going to use for writing things. And what you'll see when we do this, so let's just mess around with this. Let's do display.set pen to 15, the background color, and display.clear. So, oops, display.clear. And absolutely nothing's happened on that display down there. So why is that? It's because things don't immediately happen. We kind of like set up a load of actions that we want to send to the display. And then when we're ready, we call, what's it called? Well, I think it's actually in my display centered function that does some other maths. No, it isn't. Okay. So maybe we're doing a lot of work first and then we're calling this, let's find an example. Here we go. So we have to call display.update for it to do anything. So when I call display.update, if you watch the screen below me, hopefully it'll go blank. There you go. It goes dark because it's changing state. It goes out of focus because of the camera. But as you can see, it's blank now. We don't have anything on there. So we've started from a clean slate. How do we then write things on the display? So that's something we're going to want to do. So we, for example, might want to, here's a good example. Let's set the pen to the darkest pen, 0, and let's do all that. Let's put some text on the display. So this is the text we want to display, which is my website URL. Make it a little bit bigger. It's always a battle between size and how much stuff you can show. This is my website URL, and then this is a location on the screen, XY we want to display it at, and then scale is how big of a font do we want to use. So we're using a font called Bitmap 8. It's 8 pixels tall. Scale of 2 will double that, make it 16. So again, if we do display.text, that nothing's happened yet until we do display.update. And then what you'll see is, it's come clear now. Let's make that big as well for a second. What you'll see is we've got some text in it's 130 over and 5 down, and it's 16 tall. So we've been able to write some text onto the display. So that's a good start point. Library also lets us do things like draw shapes. So we can do display.rectangle. I've still got the black pen selected, so it should do that. So if we then do, how does display rectangle work? Let's go look at the documentation. I can't remember if it's an X, Y, and a whatever, but there is decent documentation for this. So somewhere there's a link to Pico graphics, but let's just cheat and Google it. So the underlying display system is this thing called Pico graphics. It works on all the displays. And let's have a look at basic shapes, rectangle. So it's X, Y, width, height. Great. So if we wanted a rectangle at, let's say 5, 5 and make it, I don't know, 40 by 30. Then again, nothing happens until I do display.update. This is going to add the rectangle to what's already on the screen because we didn't clear it. So we're not repainting. Well, we are repainting everything, but we're basically just adding another object to the screen. So here comes my rectangle. And as you can see, it's over there on the left. So if I then wanted to not have that rectangle filled in, I could do something like display.set1015, choose the background color pen, do display.rectangle, something like 1010. So we'll start it a little way inside that. And then we need to take, I don't know, is it 10 off of each of these? Let's try that. And then display.update, and we should get a background colored rectangle inside the rectangle like that. So we've now got what looks like a hollow thing. So we can use these to draw all sorts of different stuff. There's a circle. We've used the circle to plot the ISS position. So if I go here, there's a triangle as well, and an individual pixel, and a polygon, and so on. But let's just demonstrate circle really quickly. So go back to the dark colored pen, display.circle. Let's put it at 50-50 and give it a radius of 50. See what happens now. Okay, that's kind of wiped out the rectangle a little bit, but you get the idea. We've now got a circle on our screen. So we've been able to do all of the sort of basic stuff that we need to build the ISS interface, except for loading an image. Loading the image is actually really pretty straightforward. There's let's go back to the documentation here. JPEG files. So we need to create a JPEG decoder. We open the image file, which needs to be on the Pico somewhere. And then we decode it and tell it where to put it on the screen. So that's an XY coordinate, and then just update the screen. So fairly simple. So I just went and got the map of the Earth with the meridian and the equator such that those met in the middle, which helps us with our coordinate system. Shrank it down to tiny size that the part of the display needs. And we've got, I guess you can see it in the ISS tracker repo. It's checked in. So we go into here. Here's our world map image as it looks like on GitHub. And that renders on the device. And then what we can do is just calculate coordinates, and we'll look at that, and drop the circles over the map as necessary. And we have to like calculate the offset into the map. So where is the that long? And then add some offsets for where's the map on the screen. So the map's not at 0, 0 on the screen because that will put it in the top left. I wanted it over to the right. So you have to account for that too. But that's pretty reasonably straightforward. So I'm going to stick with Bonnie, and you'll see this is how we draw on the screen. It really doesn't get too much more complicated than that. The JPEG code, like I say, is library calls. And let's just pull this REPL down. I fall for this every time. There's like a very specific position you have to touch the REPL at. So we've got all of that. So what happens with the device is, let's go ahead and assume that it's configured It's been through that configuration process, and it can connect to Wi-Fi. So let's see what happens when it starts up in that situation. So I'm going to roll all the way to the top of this code, and we'll come down and find the entry point because there's lots of other stuff going on here. So, ooh, gone past it. Here we go. So what it does when it starts up is it draws a splash screen, which is just my URL and the image of the space station. So that's just a load of graphics library calls to set up a JPEG and some text. It paints those to the screen, and then it leaves them there for 3 seconds. And then what it does is it has a look to see if the Wi-Fi is being configured. And the way that it does that is it tries to find a file on the Pico that's called wifi.json. And if it finds that, then it knows it's got stored Wi-Fi configuration. So if it finds that, it goes ahead and opens it and reads the JSON into a dictionary called Wi-Fi credentials. And then it will basically attempt to connect to the Wi-Fi. If you want to see in detail how this whole process works, it's pretty standard MicroPython. I've done live streams about it before. But basically, we just create a wireless network connection here. We set it to active, and we feed it in with the SSID and the password. And then there's no operating system here, MicroPython. So we have to loop around doing something. I chose not to update the e-ink screen while it was connecting because it was kind of slow. And you can't update the e-ink screen like regularly. So what I did was just put some debug in there. If you're connected to Thonny or some other thing like MP Remote that shows the console, it'll print connecting while it's doing that. And then look at what happened if we got an IP address, which is the happy result. It's going to output connected to the screen, and we display this later. Otherwise, we look at some of the error cases. So again, I wanted to make this useful for people that didn't really understand technology. So if it goes wrong, I didn't want it to just say, couldn't connect, fix your credentials. Because MicroPython can tell us what's wrong. So it can tell us if the password was wrong or if they put in a SSID, a network name that either can't be seen or we couldn't connect to. So it tells them what's going on there. And basically, if we're not in the happy state of if we didn't get an IP address, then what I do is just go into a loop and wait for them to press A and C to acknowledge, okay, you messed up the Wi-Fi details. And if they messed up the Wi-Fi details, what we do is delete that Wi-Fi file because we know it's got bad information in it. Wait for them to press A and B. So these are just constants inside Pimoroni's library for this device. So we wait for both of those things to be high at the same time. They press both buttons and then reboot the machine. So it'll reboot. It'll find there isn't a Wi-Fi config anymore. It'll go into that other mode, which is set up. We'll cover later, but I want to stick to the happy path at the minute of, yeah, we've got a network connection. What are we going to do? So when we've got a network connection, what do we do with it? So this is the bad Wi-Fi connections option. If we get down to this point, then we know it's good because otherwise we'd have gone into this logic and we'd be waiting to reboot. And what we do here is basically just loop forever, periodically get the ISS position and then draw it. So I've got a forever loop here. I did say earlier that I wanted this to be something that could be reconfigured later. So if when you've got it set up for Wi-Fi, you decide that you want to change your Wi-Fi or your password's changed or whatever, you just hold down A and C. It does the same trick. It deletes the Wi-Fi file and reboots, and that's just going to put it into the setup process. If not, what it does is it basically works out how long since it last updated the ISS position. And it does that by remembering the last millisecond, or the last millisecond timestamp that it got from MicroPython, and works out if a certain number of milliseconds have passed since then. And we're doing this because these devices don't have a real-time clock, so you don't necessarily rely on having real time. So I can't say, oh, what time is it? 5 minutes later, do that. So we're basically using the MicroPython time ticks, and that has functions for telling us the difference between two ticks numbers, because it can wrap around in the case where we go off the end of the clock and start again at 0. So this is just basically saying, if it's time to run the update, there's a configuration value that says how often that is. I didn't make that user configurable, it's just in a file. Then what we do is, first off, I explicitly call garbage collector, because I built this to run for a very, very long time. I don't really know if that's needed, but there's no harm and it's not real-time performance needed. So we're saying to MicroPython, hey, clean up all the trash objects and things that have no references. Make sure we've got as much memory as possible free, because we're about to do a lot of work. Then what we do is we use queue requests, which is MicroPython's requests. It's the same as desktop Python's requests to all extents and purposes. And we build up a URL to my service. So we basically go call this service here at whatever its real Google Cloud URL is, and we pass in the user's latitude and longitude that they give us in setup, and we can expect to get something like this back. So what happens is it calls that. One of the config items it's got is the password for this service. So I pre-configured those because the user doesn't need to be bothered with that. And I also give each device that I've given out a unique one, so I can tell who's using theirs. And basically, you can expect that to bring some JSON back. So if it does, great. If it doesn't, then we've got an error. Either the service was down, or the password's wrong, or something's gone wrong on the server side with doing the maths. So we're trying to cope with errors as well. And either way, we then just call this function update ISS position. That updates the screen. And that's the majority of what we're going to look at on this device. And then we basically just record when we last did this, have a bit of a sleep, and then go back to the top of the loop of, oh, did they press A and C? Yeah, we'll reset the device. If they didn't, is it time to do the update again? And if it isn't, we just keep sleeping until it is. And if it is, we run the whole cycle again. So updating the position, by this point, we've got the data for where is it. We've got a lat and a long. We've got a distance. We don't need to worry about how we arrived at these things just yet. We've got either an ocean or a land position. Let's just call it again, see if it's over the land yet. Nope, still over the ocean. So if this was over the land, we get a different format response. But no, we're still over the ocean. And what we're going to do is display all of this information, plot it on the map. And there's a couple of complexities. So let's go to update ISS position. So this here is code that runs every time we need to plot a new position for the ISS. I'm also maintaining a short history of how many positions we've seen before. So I'm maintaining the last, it's actually configurable, but the last 15. And that's a list. And what we're doing is putting each position in the list. When we get to 15, we're knocking off the oldest one. And then we're rendering all of them with the latest position being bigger. So you'll see it shows the ISS current location as a bigger dot and then a smaller trail of previous locations. So what do we do here is, first off, the boring case, if we failed to talk to the back end properly and the data we got back is the error case, we just show a general purpose network error. I didn't bothering people with what the reason for that might be, because really there's nothing the user can do about it. So it does that, and then 5 minutes later, the main loop will try again and see if things are better. And if there wasn't an error, what we do is clear the display, and then load that map. So we just load the JPEG file worldmap.jpg that lives on the little device. And what I do is load it to map left offset. So how far across the screen is the map? 0 looks like a magic number here, so I don't like that. That should probably be, I bet you I've defined a constant for like map top offset, but that should be that, which is how far off the top the map needs to render. So let's see up the top there. Do we? Oh yeah, look. Defined it. Never bothered using it. So let's fix that. Right now. So where were we? We were loading the map, weren't we? Right. So yeah. So no magic numbers, meaningful names. So we're going to decode this JPEG and we want it displayed at this XY coordinate on the display. We don't want to scale it and we don't want to dither it. Those are just options for Pimoroni's library code. So that just adds that as a thing that needs to be drawn on the screen. So the next time we call display update, that'll appear at the XY coordinate. Then what I'm doing is to the left of the map, I'm drawing a rectangle to put all of the data in. And then I'm starting to pull information about how far away the ISS is from the service result that we got. This here just always makes it 5 digits, so it's always a fixed width. And we're displaying that at a specific location, and we're making it nice and big, scale 4. And then underneath, I've got some smaller text that just says miles away. That should probably not be a constant because the service here tells us what the units are. So I should probably at least look at that. And then in future, if I have a kilometers, I should display kilometers. So let's put a to-do in for that. What's the field called? It's called units. So we can do that. So if we ever make one of these that can be configured to kilometers, so it's for somebody that primarily works in the metric system, then this won't have this hard-coded miles. That's kind of bad product. That's lazy on my part. So once we've got the distance and we've shown that, we then have a look at where we are. So if there was a field in the response called ocean, which let's give it another go, but I bet it's still over the ocean. Oh, no, it's over South Africa. Right. So if there was a field called ocean, that contains the ocean name. We display it. So that's pretty easy. We just get a location text and set it to the value of ocean. Otherwise, we start looking for different fields relating to place names. So we might return, the service might have returned as a country name. So in this case, South Africa, a region name, which would be like a state or an administrative area. So for our long reach Australia example, that would be, did I say it was in Queensland? Sorry if I got it wrong. I think it's in Queensland. In this case, we are over the Limpopo region in South Africa. If we were in the US, it would probably be the state that we're over. So like Illinois or something. And then the locality here, if we get that, is the place name. So here we don't have enough information to get a locality. So we might not be over a town. We might be over like an undeveloped area or a bit of desert or a forest or something that isn't a place name. Let's run it again and see. Oh, we've moved now. So we're over Zimbabwe and we've still got a region, but no town name. So we might get some or all of this data. So we have to have code that builds up the location text string with this, and it has to take into account that it might have some or all of this. And it's pretty much guaranteed you're always going to get the country. The other two, it kind of depends. So what I've got here is just some code that builds up a string based on that, and it does some bits and bobs with working out how big things are because this device has got a limited amount of space. And what you'll see is sometimes it will not show some of these when it's got all of them because there isn't enough space for it. There's just some logic in there that makes sense of that. And then we have a bit of a coverall of if we can't work out where we are and we're not over the ocean, then we just say, I don't know, we tried really hard. I've never actually seen that happen in practice, but there we go. And then we just remove any trailing commas from where we built this text up, not really knowing how much of it we're going to have. So it might have ended in a comma from where I started appending things together. Strip that off. Then we want to draw it. And the nice thing is when we draw it, the library allows us to like measure it first. So how wide is this bit of text going to be in the given font? And we can get a pixel number back. And if it's bigger than the amount of pixels that I've allowed in the space next to the map, then I've put some logic in here to try and slim down the text a bit. So if there's just way too much information, it will drop some stuff that's optional. So if we got all three things, we had location, locality, town, region, state, country. If we got all three and it's too much text, then what this does is parses it out and drops the region bit. So if you got like a very long town name in Illinois, it would drop Illinois and just show very long town name USA because we don't have the space for the state. And there's some other logic that messes around with that. And basically, if it's still way too long, what we do is slice it off at a certain point and just put an ellipsis on the end. So it ends with ... and it doesn't just go crashing off into the map or something. Then what we do is just show the text like we've been doing with other things. So there is a bit of a complication here. We can tell it when to wrap the text. So I'm fitting the text into a gap to the left of the map. So what we do is we calculate how far across the screen we want to start to wrap, and it will do that for us. So we're basically saying here, wrap at the width of the display minus however wide the image is, which is over to the right there somewhere, and then however far minus how much of a left border we've got to stop the text from crashing into the left edge of the screen. So this is going to handle that for us and wrap it, and that's a useful library function. So that's all the stuff with text. Then the final thing that we need to do is put a dot in on the map. So we rendered the JPEG, and that's just in the XY screen space. So somewhere over that map, we need to put a dot for where the ISS is. We need to do this translation of, we've got a latitude, longitude, so a minus 180 plus 180 and a minus 90 plus 1 plus 90. And we need to work out where that is on our map and then where our map is on the screen to drop the dot in. So what we do is there's a little bit of maths here, but basically what we're saying is work out where the latitude and longitude fit on the XY plane in an image that is however big, and we know how big our image is, and then move those values across the screen to reflect that the map isn't a 0, 0. It's slightly off to the right and slightly down from the top. And once we have those X and Y positions, we draw a circle there and we give it a radius of 4, and that's the current one. And then what we do is we go down that list of location histories that we've maintained, so previous XY locations that it saw, and we basically add everyone as a circle that's a bit smaller. I chose to put this location history into the device because I decided it was a function of the device, not the service. I could have put it in the service, but the problem with that is you then get location histories for every time the service had been called, not every 5 minutes, which is when the device calls the service. So location histories live on the device. So when we first power it up, it'll have one dot wherever the ISS currently is. and then it will take, it's keeping 15 at the minute, so it'll take an hour and a bit to update all 15 before you get the full trail, and then it will start snaking across the map quite nicely. Then we just have some other text for when was this last performed. One other bit of information that we're using that distance away from is what you can see here is I can turn the LED on the device on or off. So if the distance is near to us and I make that configurable, so if the ISS is within, like, say, 1,000 miles or whatever of us, turn the LED on so we've got some sort of extra feedback. We can play around with that here in the REPL. So I can do this, and you'll see the little LED down there. My finger has just defocused that. Yeah, won't focus. But I think I just rebooted that as well. Yeah, I did. It's running the code now. Oops. Stop. Ooh, you're not going to stop. It's busy. All right, we'll let it do its thing. But the little LED came on. And we'll let this go back to tracking the ISS. Unless I've actually stopped it, in which case it won't be doing that. Bonnie sometimes doesn't like this, I've noticed. So that might actually have stopped running. And let's, in that case, power cycle this guy a minute and get it. See if we can get it into a state where, there we go. Right, I've got control of it now. So that's it running the splash screen. Bring the desktop back. We've got a MicroPython REPL. So yeah, where was I? I can turn the display on and off. We just need to reset the state of our REPL because the device rebooted. So we need to steal some code here, import the Badger. We need to create a display object like this. We need to set an update. We don't need to set fonts. We're not going to use that. So if I do display.led 128, that'll turn it on. You can see the little LED has gone on in the bottom left corner. Display.led 0, I'll turn it off. And I'm using that as a how far away are things. So that's a sort of tour of the happy path code. So let's see if we can run this and see if it's going to go and track the ISS and stay in focus maybe for at least 5 minutes. It's connecting to the Wi-Fi. And you see the print output that I put in the code is appearing on my console because Sonny's connected to the device. There we go. It's connected to the Wi-Fi. And it's going to go call the service. Indian Ocean. So, like I said, we've only got one dot on the map because the location history is maintained by the device. So we reset the device. It doesn't persist the location history. And over time, it will build it up. So we're 4,374 miles away. We don't have the light on because it's not near us. And we've got one dot. So that is happy path. That's what happens when it's up and running and everything's good. So there's two things we can do. I'm going to switch and look at how does the service it calls, so this one here, actually work. How does calling this get us these things, Arabian Sea right now. And then there's also the how does the user get to set this up when they first get it back on the little device and the little device doesn't know about their Wi-Fi. So we'll remove the device for the minute because it's only going to keep going out of focus when it updates. And that's going to annoy me. And we'll take a look at how the code behind this function here works. So what's happening on the server to get us this information? And to do that, I'm going to switch to Visual Studio Code, which is better for JavaScript. And like I say, I chose to write this as a cloud function for Google. It doesn't use any Google Cloud Function APIs. It's just a place you can put something that gives it an HTTPS URL that you can call it and rely on it being around and executing in a timely fashion. So if you wanted to put it somewhere else, you could stick it on Cloudflare or AWS or Azure or wherever you like, really. So we've got a pretty standard node project. And if you're aware of cloud functions, the way that they work is, let's make this a bit bigger. Hopefully that's nice and viewable. The way that they work is, let's get down to the actual entry point. So we are using a little bit of Google Cloud Functions library. So functions.http, I want an HTTP function. I want it to be called ISS locator, and then it acts like an express route or route. So what you get is a request and a response object. The request tells you stuff about who made the request. The response is what you're going to send back as a result. And there's a little bit of complication in here about CORS, so allowing this to be called from anywhere by a browser, and that involves dealing with the options method. We're not really interested in that. That doesn't apply to being called from Python. It's a browser thing. So what we do is just some basic checks. Is I'm only supporting GET requests. If you try anything else, you're going to get a method not allowed. And I'm going to tell you the only things I want to hear from you are GET or options requests. And that's the end of it. And then before we do any work, I want to check that you actually provided a valid value for my my security token. So I've got a header here that you need to give me a value of that. I know what that value is. It's in the configuration for my cloud function. And if you don't give me a valid value for that, I'm going to send you a 401 not authorized. And that's the end of it. You're not getting any data from me. So this is just to stop things being spammed by someone discovering the URL and hitting it up, and ultimately costing me money in Google Cloud and API resources. Then what we do is I need a lat and a long parameter. So I need to know where you, the user, are. And if you don't provide those, I'm going to send it back and say back request. So when we call things here, look, we provide a lat and a long. That's where I am. That's not where the ISS is. And we're going to use that to calculate this distance. The only thing we need it for is how far away are you? Then what we're going to do is pretty much the API call chain that I looked at in Postman earlier. We're going to ask the ISS API, where is the ISS? We're going to get information from that and parse it out into floats, so floating point numbers. Then we're going to work the distance out, and I'm just using a library function for the haversine formula here, which basically is a way of calculating the different distance between 2 points on the Earth. So we use the distance between the user's location and the ISS's location, and we tell it that I'm hard coding everything into miles at the minute. So we just put our response field miles in there. This mile here goes into the haversine library function I'm using. That's just off the shelf npm install haversine. Didn't need to write that. So at this point, we've got an ISS location, latitude, longitude. We've got a distance unit, miles, and we've got, what else we got? Well, a user's location that we don't need anymore. So what we don't have is a name for where this lat long is. So we haven't geocoded it. So what we do is feed that into the Google geocoder and wait for the JSON to come back. So nothing specifically too stressful here. This is just a regular fetch API call, and I'm providing my key So the Google geocoder is key located. There is a chance that I would go over my allocation for the day and get rate limited, but with a small application like this that runs every 5 minutes on a few devices, that's not happening. If it were to happen, I might want to start caching things or maybe paying for things. But there we go. If we get an API response from that and it's 0 results, then that's the case I was showing earlier where it's over the ocean. Google doesn't know anything about that. We're going to have to go call this other service, the GeoNames one, and see if that brings us back an ocean name. And if not, then who knows? And we're into the unknown location scenario. So if we don't know, if Google doesn't know, we try the oceans. If Google does know, then we start pulling some address components out of the document that Google sent back. So let's have a quick look at what that looks like. So if we are over the land, and here's long reach again. So you can see we have a results array, and that's got objects in it, and that's got an address components array. So I just wrote some code that looks for things of different types, the things that we want, and sends them back if needed. So we look for the locality and the country, and then we do some data massage on that. So some of the country names in Google are quite long, and I don't have the space on the devices to sort that out. So if you look at format country name here, it's just some utility code that looks up the country name in a map of country names that I've got, and either returns another representation of it or goes with the original if it's not in there. So what did that do? For example, here, if you're in the United Arab Emirates, I just return UAE because it's easier for the device to deal with. Equally, some that have got accented country names in Google that don't relate well to the font on the device, I just remove the accents and just shorten some things up. So if you're in Trinidad and Tobago, we don't need AND. We can just have an ampersand because it saves us some space. Similarly, St. Kitts and Nevis. And also some other common abbreviations. So St. Lucia, we can have St. Lucia with the ST rather than Saint spelled out. This is probably the longest one, Democratic Republic of the Congo. DR Congo is just fine. So we do some slight massaging on Google's data. Back to where we were. And then we look for the region. So that's that administrative area. So that will be the state in the US, or in Australia, also the state. So there we go. Queensland is the administrative area level 1. And we want the long name because the short name is the abbreviation. Except I decided that we want the long name, except for in the US, because people understand the state abbreviations well enough. So if we picked somewhere that was in the US, then this value here, for example, might be California, and this value here will be CA. So in the case of the US, I went with CA because I think people understand that well enough, and California takes up a lot of space that it's a common enough abbreviation we can use it. Yeah, and then all we do is just set the locality and the region fields if we found them in the response, add in a date for when we generated this information, and throw the response back out in the response object. So back to our cloud function here, call that. You'll see all of that work happening. And here we're in China right now, and we've got a locality and a region. So to be displaying those. And I've left it running. So if we put this back and de-blur. Come on, focus. There you go. You can see it's in the right bit of China. So this is calling the hosted version of this function in Google Cloud, which is, funnily enough, returning the same results as my local test version here. But yeah, that's how it works. So that Somebody asked much earlier, over an hour ago, do you need an individual Google Cloud account? Yes and no. You can just run a single cloud function on this. You need to turn on the geocoder API so that it can call that, but none of that stuff should cost you any money unless you were running hundreds and hundreds of these devices and or updating them like every way too often for the e-ink device. So a 5-minute update with a reasonable number of devices, this is never going to cost you any money. You do, I think, need to put a credit card on file with Google just in case, though. But you can also set up all sorts of alerts. So if I get anywhere near being charged for anything, tell me about it first. Can't remember if you can tell it to just cut the service off if it hits the limit or not. But have a look around in there. You can definitely do alerting and make sure you don't get any unexpected bills, which is not what you want. So that's our server side. And what I'm going to try and demonstrate now, and we'll switch back to VS Code for that, I think, and turn Thonny off, is what I want to try and do is demonstrate what happens when you first get one of these devices, which is something that a process that I want to reuse in a few products for this. So let's see if we can first off make the device bigger, and I'm going to power cycle it. They do provide a really handy reset button on there. So did that work, he says? Yeah, so it's reset, it's rebooting, and let's just get it somewhere where we can see it and let it do its thing for a minute. Hopefully stay in focus. It's connecting to the Wi-Fi. If I was doing a stream this long, I'd have brought more drinks. Right, so it's connected to the Wi-Fi, and this should be nothing we haven't seen before. It should start tracking the ISS. He says, hopefully, there we go. So we're still over China, 4,061 miles away. But what I wanted to show as a sort of final thing with this is how would you put this in someone's hands without knowing their Wi-Fi credentials or other secrets? So remember, I've got some code in here that if you hold down A and C, it deletes a file on the device and reboots it, and then it detects, oh, I'm no longer configured. I need to be set up on a Wi-Fi. So we'll see how that works, and let's hope it does work. So press A and C, it's rebooted. What's happened now is it shouldn't connect to the Wi-Fi because it no longer knows about the Wi-Fi. There we go. So it's gone into its setup mode, and it wants us to connect to a Wi-Fi network called ISS Tracker. So this is exposed an access point, which is a Wi-Fi network that's not connected to the internet. It's the Pico on the back of this device. And there's a tiny web server running on there that uses another Pimoroni framework we'll look at. And that's now waiting for us to connect something to it. So we have to join this Wi-Fi with a device. It will then pop up like when you're in a cafe, and you'll get the portal that will allow us to put in the real details. And then we'll save them, and hopefully it'll reboot and come back to where we want it to be. So I'm going to try and do this, and the silly thing to do would be use the Macintosh to connect to the access point, which would immediately cut this live stream because that cuts me off from the internet. So we're going to try and use the trusty iPad here, and let's see if we can get that up and running. 1 second. So if anyone's wondering how I'm sharing the iPad, and if you've got any better answers to this, I would love to know it. I am using QuickTime and doing a movie recording of the iPad that I never hit record on. And that allows me to put the iPad screen onto the Mac screen. And that is how we get to this sort of situation. So what you see in this window here, see that movie recording? That's actually QuickTime. And what's going on here is the iPad. So what I should be able to do is get rid of that and start messing around with the iPad's connection. So what we can see is I am on the Wi-Fi at the minute, and there is that other Wi-Fi there called ISS tracker. That's the device below. So if I take myself off of my own Wi-Fi and connect to ISS tracker, what you'll see, haven't tried this on this version of iPad OS, so we'll see how this looks, is it's logging into a captive Wi-Fi. So it's kind of like we're at the cafe or something. But this is a captive Wi-Fi that's on this tiny little Pico on that display. Nothing's happening down here on the display by design. So it's served as a web page, and it's picked up. I just went with the mouse to click on that. I need to use the iPad because this is just a view. This is not like a remote desktop session. So it's picked up a Wi-Fi SSID, and it's picked up all of the other ones. So we've got some code on the Pico to say, hey, go scan all the Wi-Fi SSIDs you can see. And it also allows us to put another one in there. So I've written some code that if you hit that, will open up a text field. So if we do other here, we can manually enter one. Or we can, hey iPad, don't do that. Hey, come on. It's trying to draw things when I want a, I don't want that. I want that. Right, there we go. Or it's had a good guess and gone, oh, the one that's got the highest signal strength, that's probably the network you want to connect to because that's the one I've got the best signal for. And then we can put in the Wi-Fi password. And let's do that with a keyboard. And the Wi-Fi password for this guest here is going to be right. So that's that. And oh, I went ahead and saved it, but there was a lat long option down there where you could put in your lat long. I would love to be able to show a Google map for that, but can't do that because it's not connected to the internet at the time. So I can't use the browser API to determine where you are and stuff. So what you'll see has happened is, so the iPad has disconnected and it's gone back to the Wi-Fi it was connected to. The ISS tracker Wi-Fi has disappeared from the other networks. And then down there, down the bottom, the ISS tracker itself, I'll just get rid of this because it eats some resources. The tracker itself has gone out of focus because it went away and went through the normal boot up process, successfully connected to the details that I'd given it. And it's now telling us where the ISS is over China. So the last thing to look at, and I'm going to do it in VS Code so we don't disturb this thing, is how does that work? And I've done a live stream on this before, so I'll sort of do it at a high level. But if we have a look in the Badger code here, you will see that when it starts up, what we had was the first thing it does is looks for this Wi-Fi file. So if that's not there, which is the case when I ship it to you, or when you pressed A and C and reset it, then it's not going to run this block of code here. It's going to come all the way down here, fall into the exception case, and it's going to run whatever's in setup mode. So we should be able to skip around more easily in VS Code. So what does setup mode do? So setup mode presents that information on the screen that we saw, connect to a Wi-Fi network, and then the name of the access point it's going to use. I made that configurable, so it's in the config. And then what we do is we again start up the Wi-Fi connection and make it active. But instead of trying to connect to something, this time we say, okay, scan and tell me what SSIDs you've got. And then we basically parse out the results of that, get the SSIDs. And I can probably remove that because I know this code works. So let's get rid of that. And then if we found some SSIDs, what we do is look for the signal strength. So what comes back for each network is a dictionary, and one of the things is signal strength, RSSI. And basically we can store that information against the SSID. So we're storing like SS mesh and then how strong that was, and the next Wi-Fi and how strong that was. And then I just run those through Python sorted to basically sort them by that key. So we get a data structure that has a list of the Wi-Fi networks with the strongest one first. So that's all well and good. But then what happens? We define some stuff that we'll come back to. So let's just get rid of this. We then use something called Pimoroni's View framework, which is a web framework from MicroPython. So it's a little bit like Flask. We define a server and we say, okay, I want when the /route, so the home page is hit, I want to run this function, AP index, when it's a GET request. And then when the configure route is hit, I want to run AP configure, and I expect that to be a post. And then we have a catch-all for all other URLs. And all I'm doing is just pushing all of those straight to the index page. And then what we do is start an access point with that. We'll look at all of that. And we run Pimoroni's DNS server to basically say, oh, we're just acting as the web server for the device that connects to us now. And we're just basically going to say everything routes to us, everything goes to the home page. And then we're running the server and just displaying the text on the screen that says, hey, go connect to ISS tracker or whatever we called it. So when somebody does connect to that Wi-Fi, what happens is they basically land at one of these methods. So if they land at something that isn't / or configure because their device tries something else, a lot of devices try some known URLs to see if an access point is connected to the internet. If they hit any of those, we redirect them back to our home page by sending out an HTML page that just does that. It just does client-side redirect. Again, the details for this are in another stream. But eventually, we're going to land on the index page. And what happens then is, if all's good, we just render out the index template. The framework has a nice templating system. So in here, I've got the HTML for my index page. It's got some really minor styling on it. And I've actually sort of, to make this really quick and dirty, included all the styling as another HTML page, and it just pulls it into the head here. So there's all of my styles. It's a mess. But these are tiny devices, so we want to optimize things. And I didn't want to write another route just to serve a CSS file. So I just pulled it in here. So we get one big index HTML that has all the styling. That's your page there. And this is basically a web form with some, again, inline JavaScript. Like, okay, there's JavaScript and CSS in the HTML, but it's a tiny device. And the tiny device, I didn't want to write another route, forget a JavaScript file and store a JavaScript file in here. So we just put it all in together. So basically the entire front end for presenting the form to the user, saying what network do you want, renders out through this template. The View framework handles passing in all of the available networks as a parameter to this template. And then what you can see is somewhere here we have a select, and what that does is renders out all of the values. So So we've got a loop here that just loops over the networks, renders out drop-down values for each of those. And then we've got some JavaScript that captures the submit and does some stuff. And it posts all of that back to another endpoint called, what do we call it? Called /configure that expects a post. When that gets hit, this gets run. And what happens here is we just get all of the form values, dump them in that Wi-Fi file on the Pico. So that will create it. And then we just restart the machine and tell the user that's been done by sending another web page back that says, oh, okay, it's ready, it's rebooting. So the experience on the phone or the iPad will be, it's ready, it's rebooting. The machine, the little Pico itself will reboot and try and connect. If you give it the correct results, you'll get the correct values. You'll get what you see down there. It goes into running the application. If not, when it starts up, it will either tell you you've got the password wrong or the SSID wrong. And then it will basically wait for you to press A and C to acknowledge that. And it will reboot with that file blown away. And you'll go back into the, okay, let's connect to the network and configure it. So that's how we get a more polished product. And I would like to make this sort of startup sequence a bit of a library so it could be used with something else. So you basically had, import whatever my library is, and then you had some code in your application that was basically, if we need to be set up, run the setup portal, else run my application, and then you just implement run my application. I'd like to get around to doing that. It's going to take a little bit more making it generic, but the more things I build with specifically these Pimoroni Pico onboard devices, and let's find the browser. We should have. If we go look at these, the more stuff you build with devices like, well, any of these really. I mean, some of these you plug the Pico into, so like the display pack, you need a separate Pico. The GFX pack, you do. These sorts of things, you don't. Pico W, a board logo here means it's built in. So like all of these three, for example, the big e-ink, the little e-ink that we saw today, and the cosmic unicorn, the big one, which we've got one back here. All of those could work on the same sort of general setup process of, am I on the Wi-Fi? No, but I need to be. Pop up an access portal with a nice portal. Ask the user for the Wi-Fi credentials, and I probably need to make some other way of expressing what other things you need from the user. So, for the ISS tracker, we need make the ISS tracker big. For the ISS tracker, we need a lat long, and for something else, like it was cheer lights or something, we might need some configuration. Like, do you want me to show cheer lights on all of the LEDs, or do you want me to show the history or whatever? So there'd be some like application specific configuration. Don't know how that would work, but that's the fun of building a library. We'll see how that goes. So I can't promise I'll do that, but I've got lots of need for it, so I'll probably end up getting built as a result of different projects. So yeah, we've been doing, here it goes again. Where are we now? North Pacific Ocean. As you can see, it spends a lot of time over the ocean. It would be nice, Google, if your geocoder knew what oceans were. But anyway, so this says I've spent 2 hours and 10 minutes going on about ISS tracking and stuff. So hopefully that's useful, but I'm going to wrap it up now-ish. And if you want to see what is coming up in the future, the best thing you can do would be go to Twitter, which we're still calling it on this channel, and you'll find stuff there about what I'm up to. If you like coding things, go to GitHub. And to be honest, probably the easiest thing to do is just go to the website, because there's a link to all of those things from there. So hopefully you've enjoyed this. If you have, I would appreciate it if you don't mind buying me a coffee. I don't literally buy coffee with this stuff. It generally funds sensors and other things for the channel, as does periodically selling off bits and bobs that I've used on the demo. So I recently sold off the Atom Matrix to somebody on Twitter, and I'm hoping they have fun with that. I sold off the Advent calendar to somebody on Twitter, and they're definitely having fun with that. I am going to keep this fella because I've got lots of uses for it, and it's part of my plane tracking system, which is like an ongoing demo. And I also kind of want to have a go at maybe making some more of a product of this. So yeah, this one's not for sale by me. If you want one, go to Pimoroni and grab one. Or if you're in the US, you can get them from Adafruit if you want somewhere with more local shipping. But Pimoroni will ship them globally as well. I don't know what works best if you're in the US, but you've got options. So there we go. And thanks, Pierre, for coming along. I appreciate you sticking with it this long. I didn't have a sort of how long is this going to take plan for this thing. It just worked out. It was 2 hours, which I think is the longest one of these I've ever done. But and yeah, if you do build something like this, I would love to see it. There's somebody building this similar project on the M5 stack dial, which is a really nice sort of round thing that's got a rotary encoder dial around the outside of a round screen, which is color, and I guess it's some sort of LCD screen. It's much faster than the e-ink. So I'm following that to see how that goes, because that looks like a lot of fun as well. Anyway, that's enough for today. So what you should do is go to the website and have a look at things. You can do the usual follow things on YouTube and so forth if you like your notifications that way. But I will leave you to the rest of your day, and I'm going to go deal with some admin around car parking. So fun times. All right, take care. Bye.